This is 6.1.2 Linear Algebra for Computing. In this section, we'll talk about norm of a vector and unit vectors. The norm of a vector actually indicates the length of the vector, or sometimes instead of using the word length, we can also use the word magnitude. And basically, it is a value that indicates how long this vector is. In our study, we are interested in the norm, as in the Euclidean norm, basically. And in the Euclidean norm for the R2 space, we can look at this example. We have the vector v equals to R2 with v1 in the x-axis and v2 in the y-axis. In our case, x and y are perpendicular to each other, and we can employ the Pythagoras Theorem to find the longer side. The longer side, which is the length of v, is equals to v1 square plus v2 square. If you square both sides, what we'll get is v square equals to v1 square plus v2 square. Over here, the equation v, to be more precise, we should have saying that it will be the norm of v. And hence this equation is norm of v square. Hence equation 1 is the equation for the Pythagoras Theorem solution of the length for R2. We now extend the Pythagoras Theorem for R3. We have vector p with tuple R3 as v1 in the first coordinate, v2 as the second coordinate, and v3 as the third coordinate. If we study this right angle triangle, then we will see that the length of v can be found by knowing the length of rp square and OR square. I'll write the equation again. The norm of v is equals to rp square plus OR square square root. If we square both sides, then it will be norm of v square equals to rp square plus OR square. We can calculate OR square, which is using this vector. The OR square is this vector's length. It can be calculated using OQ square plus QR square. I repeat, OQ square plus QR square is equals to OR square. Therefore, RP square plus OQ square plus QR square equals to the norm of V square in the R3 example. Now, motivated by the pattern from first equation and the second equation, for Rn, the norm of V in Rn is represented by this equation here, which is taking the square root of all the entries square, sum. Let us see example 1 for an example in R3. We have the position or the coordinates, first coordinate as -3, second coordinate as 2 and 1. And remembering using equation 3, we basically take the square of each of these coordinates sum it, and finding the square root. And the answer is 14. What is obvious now is that even if we have negative coordinates, because it will be squared, therefore the entries that will be summed will always be positive before being square root. Therefore, the final solution will always be positive value and can only be 0 when all the entries are 0. In the next slide, we now will summarize some properties regarding norm. The first property is that it is a positive value. It will be 0 or greater than 0, and it will only be 0 when the vector that is being evaluated is the vector, the 0 vector, where all entries are 0. The third property is a scalar k multiplying by the vector v. What is its norm? And the answer is that its norm will be the absolute value of k, the scalar, multiplied by the norm of v. Let us prove this property. We now treat kv as an entry of k v1, k v2, k vn. Basically, we distribute the scalar k into the coordinates. We then apply equation 3, which is the Pythagoras Theorem, basically squaring each entry, k v2 for the second entry square, plus k vn for the last entry, and taking its square root. Now, by the law of exponent, which we recognize a square b square is equals to ab square, we convert each entry into its individual part, and then we distribute the addition of each of these vector element coordinates multiplied by k square. And again, using the law of exponent, that is, the square root of ab is equals to square root of a multiplied by the square root of b. We can extract k square out, and applying square root will get absolute value of k. We recognize that the second expression is reduced, or it is identical to the norm of v, and hence we get this final expression, which is a scalar value k multiplied by a vector v, and its norm is the same as the absolute value of k, the scalar, multiplying by the norm of v. This slide shows a summary of rules of exponent which we have just used. The rules of exponents we are using is from powers of a product rule.